Hello everyone. Today I'm going to present YOLOv6 and YOLOv7. Let's start with YOLOv6. YOLOv6 is a single-stage object detection framework for industrial applications. Since the previous versions of YOLO have been already covered, I will only be covering the modifications prevalent to YOLOv6 and YOLOv7. So let's begin with the YOLO network. The network design of the sixth version consists of an efficient backbone with rep VGG or CSP stock rep blocks, pan topology net, and an efficient decoupled head with a hybrid channel strategy. The modifications include a new backbone based on rep VGG called efficient rep that uses higher parallelism than previous YOLO backbones. Compared with other mainstream architectures, rep VGG backbones are equipped with more feature representation power in small networks at a similar inference speed, whereas it can hardly be scaled to obtain large models due to the explosive growth of parameters and computational costs. The neck of YOLOv6 adopts pan topology similar to YOLOv5. The head of YOLOv6 is called efficient decoupled head and uses a decoupled head architecture. In this regard, a decoupled head means that the detection and classification heads are separate from each other. So let's take a closer look at YOLOv6 architecture. Some previous object detectors used multi-branch networks because they often achieve more classification performance than single path ones. But often it comes with the reduction of the parallelism and results in an increase or inference latency. On the contrary, plain single path networks like VGG take the advantages of high parallelism and less memory footprints, leading to higher inference efficiency. YOLOv6 uses a rep VGG called efficient rep, which is a structural reparameterization method to decouple the training time multi-branch topology with an inference time plane architecture to achieve a better speed accuracy trade-off. We can see the backbone here, which consists of the rep VGG block here, and those are stacked together. So each rep block is converted to stacks of 3x3 convolutional layers denoted as repconv, which we can see here, with ReLU activation functions during the inference phase. Efficient rep backbone sufficiently utilizes the computing power of the hardware, resulting in a significant decrease in inference latency while enhancing the representation ability in the meantime. To achieve a better trade-off between the computation burden and accuracy, a CSP stack block is introduced to build the backbone of medium and large networks. CSP stock rep block is introduced is composed of 3 1x1 convolutional layers and a stack of sub-blocks consisting of 2 rep VGG blocks or repconv with residual connection. A CSP connection is adopted to boost performance without excessive computation cost. The loss function is composed of a classification loss, a box regression loss, and an optional object loss. YOLOv6 introduces varifocal loss for classification and SIOU or GIOU loss for regression losses. Varifocal loss, VFL for short, is a derivative from focal loss, but it treats the positive and negative samples asymmetrically. By considering positive and negative samples at different degrees of importance, it balances learning signals from both samples. SIOU and GIOU are the IOU series loss function, which regresses the 4 bounds of a predicted box as a whole unit. Among other improvements, YOLOv6 extended the training period from previous 300 epochs to 400 epochs to reach a better convergence. YOLOv6 introduces self-distillation to improve the model accuracy while not introducing much additional computational cost. Basically, it is a knowledge distillation technique, minimizing the KL divergence between the prediction of the teacher and the student. Also, YOLOv6 introduces a quantization scheme for detection using rep optimizer and channel-wise distillation that help to achieve a faster detector. So let's go over YOLOv7. So the most important modifications of YOLOv7 include the trainable bag of freebies methods and architectural reformation. In its architecture, YOLOv7 introduces an extended ELAN architecture instead of rep VGG as in YOLOv6. So here we can observe that the backbone is practically similar to YOLOv6, but the rep VGG blocks are changed to ELAN blocks in its backbone of YOLOv7. So ELAN is a strategy that allows a deep model to learn and converge more efficiently by controlling the shortest, longest gradient path. YOLOv7 proposed ELAN that works for models with unlimited stacked computational blocks. ELAN combines the features of different groups by shuffling and merging cardinality to enhance the network's learning without destroying the original gradient path. The 7th version of YOLO adds compound model scaling, which is aimed to adjust key attributes of the model to generate models that meet the needs of different application requirements. For example, model scaling can optimize the model width, depth, and resolution. In traditional approaches with concatenation-based architectures, different scaling factors cannot be analyzed independently and must be considered together. For instance, scaling up model depth will cause a ratio change between the input channel and output channel of a transition layer, which in turn may lead to a decrease in hardware usage of the model. But YOLOv7 introduces compound model scaling for a concatenation-based model. The compound scaling method allows to maintain the property that the model had in the initial design and thus maintain the optimal structure. Compound scaling works as follows. Scaling the depth factor of a computational block also requires a change in the output channel of that block. Then width factor scaling is performed with the same level of change on the transition layers. YOLOv7 architecture contains a backbone, a neck, and head. The head contains the predicted model outputs, but YOLOv7's architecture is not limited to one single head. The head responsible for the final output is called the lead head, and the head used to assist training in the middle layers is named auxiliary head. In addition, and to enhance the deep network training, a label assigner mechanism was introduced that considers network prediction results together with the ground truth and then assigns soft labels. Compared to traditional label assignment that directly refers to the ground truth to generate hard labels based on given rules, reliable soft labels use calculation and optimization methods that also consider the quality and distribution of prediction output together with the ground truth. Thank you for listening.